Hey, good afternoon, everyone. Any issues with Lab 2? Did you all get Lab 2 done? Okay, so today I've got Lab 3 assigned on Dropbox. I'll talk more about that today. As I mentioned last week, there's a big jump in difficulty from Lab 2 to Lab 3, because in Lab 3 we're going to be implementing a kind of a minimal version of the CPU. So there's a lot of details for this lab. So we have 3 weeks for lab 3. Okay. Hopefully I'll get far enough today for you to be able to get started on it. So last week I was talking about sequential logic, and the reason I was talking about that, of course, is the CPU is a collection of sequential logic and combinational logic. So we're going to have an instruction memory in there that's going to be a ROM, single-ported ROM, and the size is 4096 by 32. So it'll have the capacity to store 4096 instructions, and it'll have an address which will be fed by the program counter, and that will be word address. So the program counter will increase by 1, and you'll get the next instruction out, right? And then we won't have a data memory, but we will have some registers in there that will be implemented as basically multi-bit flip-flops. And then we'll have some combinational logic in there as well. And you guys have already you've already designed combinational logic in Lab 2. Okay, so I mentioned that the sequential logic is implemented with always. I think that's, as far as I know, that's the only way that you can build sequential logic in Verilog. And so in the case of sequential logic, you have always at, and then generally if it's a edge sensitive memory, you'll have pause edge clock, or you can also put neg edge clock depending on if you want it to change on the rising or the falling edge of the clock. In this class, we just use positive edge for everything, except for test benches. Test benches, sometimes we use negative edge for test bench. And also be aware that you should use the non-blocking assignment whenever you have sequential logic. That's it's not required, but it's by convention. And in this class, that's the easiest way to stay out of trouble. Okay, so in this case, we have always a pause edge clock, A gets B. So what ends up happening there is that if B and A are both updating on the rising edge of the clock, then what will end up happening is that when you simulate this, you're going to find that there's a 1 cycle delay for A relative to B. So anything that's on B will appear on A in the next cycle. So this creates essentially a pipeline register, if you remember that term from 212. Hopefully you talked about pipelining. So I like to think of it as A is like the old value of B, right? The historical value of B. Make sense? So A is the value of B pushed into the next cycle, pushed 1 cycle into the future. Make sense? Okay. Okay, so skip ahead here a little bit. Now you can also have logic like this where you have an always block sensitive to the rising edge of the clock, and then instead of just having an output that gets the value from an input, creating that 1 cycle delay, you can also have things in there like a counter, right, or a state machine. So this is the form that your program counter is going to take. So your program counter is going to increment the program counter every cycle, right, on the rising edge of the clock. And then that program counter is going to be used as the address input for your instruction ROM. Okay, so there's going to be, you can think of it like the program counter creates a 1 cycle delay, and then the program RAM or ROM is going to add another cycle of delay. Make sense? So it's going to take a cycle to increment the program counter and another cycle to read the whatever was addressed by the previous value of the program counter. Okay, and so the instruction RAM is going to be I mentioned 4096 by 32. This is showing a 1024 by 32, but the only difference there is in the address width. So if you take this address and you go from 10 bits to 12 bits, it'll increase the depth to 4K depth, 32 bits wide. Now you could go, if you want, you could create a larger instruction memory if you want. I mean, obviously we have a limited amount of memory on the FPGA. I don't remember how much it has. It's like 128 kilobytes or something like that. If you make a 4K by 32, that's 4 times 4, 16 kilobytes. So I think that's 16 out of, I think, the roughly 128 or so. So you have some, you could make it bigger if you want. But the programs we write in here won't require anything large. In fact, you have an idea of how large your program is going to be. It's going to be the square root code that you wrote in Lab 1. And that code was what, about 100 instructions generally? So you don't need anywhere near 4,000 instructions. Okay, so this is the RAM. I already covered that. Okay, and then I think the last thing I talked about on last Monday was the register file. So the register file is kind of strange because it's a RAM that has 3 ports. You can do 3 accesses simultaneously, but 2 of those have to be reads and 1 of them has to be a write. It doesn't have to be a write. I should say 2 of the ports are always reading, and the 3rd port can optionally write, but its only function is to write. And this is designed to match the instructions, the instruction set architecture for RISC-V, where you have R-type instructions that want to read 2 registers and write to 1, right, in one instruction. Now we make the register file, we make that asynchronous for the reads. So the instruction is fetched, and once it's fetched, you're going to read the 2 source operands. Why? Because they exist. The instruction is inside the CPU, and we're going to tie the fields, the RS1 and RS2 bit fields, directly into the read address 1 and read address 2 inputs, which are your 2 read ports. You guys with me? And then immediately after that instruction appears and the addresses go in, you're going to get read data 1 and read data 2 out, which is the corresponding contents of the 2 source registers. Some instructions only have 1 source register, in which case you're just going to, you're going to ignore read data 2 because that's going to be, a don't care. Now, why do we do that? I actually forgot. I don't remember. I think the reason we do that is so we could move branch resolution up as early as possible. So the idea is that if you make the register file asynchronous, you can read the registers and then do something with them in one cycle. Right? Now, if they were synchronous, you wouldn't be able to use the registers in the same cycle that you read them. You'd read them, it would take a whole cycle to read the registers, and then you'd have to wait to the next cycle to do anything with them. But if the reads are asynchronous, you can access the registers and then do something with them in the same cycle. That's the difference. And in this class, we want to be able to resolve branches, and we're actually going to do the execute. When I say execute, I mean whatever operation, whatever number crunching operation the instruction requires. We're going to do that in the same cycle that we read the registers. Does that make sense? Now, what is the downside to that? The downside is that I think that, well, there's a possibility, it's not for sure, but there's a possibility that that's going to increase the critical path delay of the design and it may limit our clock rate. But I don't even know if that's the critical path delay. It may or may not be. We never looked at that. We should. But if we wanted to run the clock faster and that was the critical path delay, then we probably would want to make this an asynchronous register file. Yes?
What is V?
Oh yeah, good question. So, Okay, so I talked about read address 1 and 2. That's pretty much just connected directly to the two register fields in the instruction. Same thing with write address. That's connected to the destination field. But write enable is telling the register file to write. And so how many instructions write a register? How many of the instructions write a register? Pretty much all of them, right? Almost all of them. Almost every instruction results in the writing of a register. The ones that don't are branch instructions. Like if you do a branch or a jump instruction, then you're just changing the program counter essentially, right? You're not changing one of these general purpose registers, register 0 to 31, right? So branch and jumps don't change a register, and store instructions don't. Not that we're implementing those, but like a store instruction that writes to memory, that doesn't change a register. I mean, some CPUs do. Like some CPUs have an auto increment. So some CPUs allow you to store something to memory and then automatically increment the address pointer, right? In which case, those would write to the register file. But that's not really a RISC type instruction. That's more of a CSCE instruction. I don't think RISC-V doesn't have anything like that. MIPS doesn't have anything like that. ARM might. I think ARM might have that. But that's kind of a, you guys follow that? Like if you store something to memory, it would be nice if you could automatically update the address, so then you could just do another store to go to walk to the next location, right? But that depends on if you have instructions that support that. But in RISC-V, if you store, you don't change a register, you only change the RAM. You only change the memory. And branch and jumps, what other instructions are there that don't change a register? Very little, very few, right? So what that means is, to answer your question, the write enable is going to be high 90% of the time, 95% of the time, that write enable will be high, meaning that you're going to be writing a register almost every cycle. But you have to have the ability to set it low in case you're doing a branch, because you don't want to inadvertently trash a register when you're executing an instruction that's not supposed to be writing to the register file, right? That's what that's for. It's protection. Like if you, on the rare occasion that you execute one of these instructions that doesn't write a register, you don't want to accidentally overwrite a register, okay? And then the write data is the value you're writing. So if you're reading, the data is an output, but if you're writing, the data is an input. So if I'm reading, I put an address in, I get the data out. But if I'm writing, I got to put the address in and the data in, right? That's the reason why this data is an input and these two datas are an output. Okay? And then that code is you can use that code. Oh, and I mentioned last time too, the reads are asynchronous, so I used an assign, because assign is only for combinational logic. I could have put the reading in an always, and in fact, I think the register file that we give you actually does do that. So if you guys look at the code that we get, like we give you the register file in the skeleton, the project skeleton in the tar file. So if you look in there, it'll look a little different than this, because I wrote this one and my student Charles wrote the other one, and Charles didn't like my coding style. He thought he always criticized my style. I don't know, he thought this was not readable, which it kind of isn't readable. I agree with him there. But he wrote his code a little bit more verbosely. But it behaves the same way. If you read from 0, address 0, register 0, you're always going to get a 0. If you try to read and write to the same address at the same time, it will perform that bypass. So it'll short circuit the write data, and either the read 1 or read data 1 or read data 2 or both in that situation, right? Why? Because it takes a cycle to write, but if you're reading and writing at the same time, you can't afford to wait a cycle. So you gotta take whatever's being written and you have to shoehorn it out to the read data out immediately, because you don't have that one cycle it normally takes to write, right? It takes a cycle to write, right? It takes one cycle to write, but 0 cycles to read. And therefore, because of that, we have to have this little hack in here, okay? Okay, so that's the register file. I don't know if that's the best way to do it. Now, when you synthesize this, it's going to get synthesized as an array of flip-flops because there's no memory, there's no RAMs on the FPGA that will behave this way. You actually have there's two kinds of RAMs on an FPGA. There's block RAM, which has 2 ports and has a synchronous read. So this has 3 ports and an asynchronous read, so this won't go into block RAM. Then you have something called distributed RAM, which is where you use the lookup tables, which are normally used for the gates, right, to create gates. You can use those as a RAM as well, but they only have 1 port. But they do support asynchronous read, but we have 3 ports. So this code disqualifies any of the specialized RAMs from being used. So what it'll end up doing is just creating a bunch of registers and then connecting them all together with a mux and a decoder. So this is very expensive. Like hardware resource-wise, this is probably 10 to 100 times more costly than if we had mapped this code into an actual RAM, right? But that's okay because it's 32 by 32, it's pretty small. And that's the reason why register files are usually small. Yes? Yeah, you could. It would still be synchronous then, technically. Just be synchronous on 2 different clocks. But yeah, you could do something like that. People have done that. Yeah, they've in fact, I think in some architecture textbooks, that's the way they do the bypass, is they say that you write on the falling edge and you read on the rising edge. And so if you have, so that way they could make it synchronous, but they could still achieve this bypass behavior, right? So you can have an instruction, you can read and write at the same time, right? But maybe that's a better way to, we could have done it that way too. That's possible. It still wouldn't go in a RAM though, because the 3 ports. The 3 ports is what's preventing, that's the main reason why we can't put this in a RAM, is there's 3 ports. Then you might say, well, is there any advantage to making it synchronous? Yeah, you'd still get an advantage though, because you'd still have more time. You'd have more, you'd give it a whole cycle to access the RAM, as opposed to now, you have to fit in accessing the register file and doing the ALU operation all in one cycle. That's more work to do inside of one cycle, right? And the amount of work you do in each cycle is what determines the clock frequency. Okay, so then there's the ALU. This is a combinational logic circuit. We're going to give this to you as well. This thing performs, I think 13 or so operations. But the operations it performs is based on the opcode, which is 4 bits. So there's 16 different opcodes. Now, by the way, this is not the opcode from the instruction. This is just a generic term, opcode. It's a 4-bit signal you give to the ALU, tells it what to do. But there's only 13 things it can do, but yet there's 16 different opcodes, right? 2 to the 4th power. So some of them are redundant. Like, for example, check this out. If you set the opcode to 1101 or to 1110 or to 1111, it does the same thing. It just checks if A is less than B in an unsigned comparison, right? Likewise here, if you do a 1010 or a 1011, it does a right arithmetic shift, right? So these 2 opcodes map to the same function, right? And these 3 map to the same function. So what can it do? It can do bitwise and or XOR. With MIPS could do. There was a 4th. No, it wasn't not. It was like XNOR, I think, or NAND. I forget. MIPS had a 4th one, but RISC-V just has those 3 logical operations that are in hardware. Of course, you could do pseudocode, to do other things. But it can do AND, OR, XOR, and then it can do add, subtract. Now, you might remember from MIPS, one of the crazy things that MIPS had was it had a signed and an unsigned add and subtract. which is crazy. And I say it's crazy because arithmetically, there's no difference between signed and unsigned add and subtract. It's the same thing. But in MIPS, the difference is that MIPS had a overflow exception. So if you did an add or subtract, you could potentially get an exception. Right? Meaning like your program would crash, essentially. Right? You would run code and it would crash if you got an exception. Most CPUs don't have that. They don't check for overflow or underflow for integer, add and subtract. Right? Meaning if it happens, your program produces the wrong result, but it doesn't crash. MIPS had this exception that would literally go into the operating system and then cause the operating system to kill the process, right? But they got rid of that in RISC-V, thankfully. And then we have multiply. There's the low multiply, and then of course the two high multiplies that correspond to the mul-H and mul-HU. Obviously that's different from MIPS. MIPS had a high and low register, you know, when you did the multiply to produce 64-bit results. You might notice there's no divide because we haven't figured out how to implement divide yet, frankly. I mean, it's possible. But I think the problem with divide is, the last time I checked, if you try to do divide in a combinational logic circuit like this, in other words, try to do divide in one cycle, it's very expensive, right? Divide, if you do a divide, you probably would want to do it across, you'd want to make it a multi-cycle operation, right? In which case, in this project, it would complicate this lab because then you would have to have a mechanism for stalling the pipeline if you encountered a divide, right? Which is doable, it's just more challenging. So we don't have a divide, but we have the left shift, right shift. And by the way, shifting is pretty expensive too. This is a barrel shift operation. It's expensive to shift, like to shift by an arbitrary amount in one cycle. But we've never had a huge issue with that. And then comparison, A less than B. We don't have B less than A because, you know, if you want to do that, you can just swap your operands. Okay, any questions? Yes?
So you connect up the output of the reads from the rec file to these A and B, and then the output of the ALU to the write data on the... Yeah,
basically, yeah, you got it. So
you don't need a mux anymore because we're not going to store?
No, well, you do need some muxes, but that's a good point. Is there a mux going into the write on the ALU? Yes, there is. There's still going to be a mux. Yeah, I'll talk about that because of we have an I/O instruction. So you need a mux for the write data because we need a way to get the switch values on the FPGA board into the register file. So we need a data path for that. I'll talk about that in a minute. But yeah, you got it. I mean, pretty much you've kind of summarized what this lab is all about. It's essentially, we're going to give you the ALU. You just have to connect these things together. And you're right, the read data read data 1 and read data 2 are connected to A and B, right? So yeah, that's your goal, is to figure out those connections. Okay, this is the ALU code. I believe this is the one that we actually give you. So I've split it into two columns. So you can see there's some weird stuff going on here. Some of this stuff, even not totally clear on. So you'll notice that when we do a multiply here, you know, we're multiplying logic types, right? Logic types are not signed or unsigned, right? Logic is logic, right? However, apparently, and we learned this the hard way, that if you use the multiply operator in SystemVerilog, it's going to interpret that as an unsigned multiply, which kind of makes sense, right? But then if you want to do a signed multiply, how do you do it? It took us a little while to figure out that you have to use this $signed, you have to typecast the logic to signed, right? But I'm not even sure. I don't know. I should look this up. But if you use $signed A, that still gives you a logic, but it's just treated as a signed value for the purpose of the multiply. But it doesn't change its type to like a signed integer, right? Because I don't think integers are synthesizable in Verilog. That makes sense? But yeah, you don't have to worry too much about this because we just give you the code. Also, the shifter was kind of strange. So Verilog has a shift operator, but we couldn't make it work. I don't remember the exact problem. I think it was, yeah, I don't remember the issue was, but in this case, we had to manually implement the right shift. Yeah, we had to do this concatenate, this logarithmic concatenate. So notice what we're doing here is we're using blocking assignment statements here in this always, right? And so we set A to be shifted, so A goes into shifted, and then we check bit 0 of the shift amount. And if that's set, then we shift by 1 bit. Oh, this is the signed, right? So we take the signed bit, which is A bit 31, and we shift that into the left-hand side, and then we take shifted 31 down to 0, and we put that on the right-hand side. So obviously bit 0 goes away, gets shifted off. And then if bit 1 is set, then we shift whatever the result of that was by another 2, right? Okay, so this is creating a arithmetic right shift. The logical left and right shift, we just use the operators, the Verilog operators. But for some reason, we couldn't make the arithmetic right shift work. I don't remember, couldn't make it work, so we just built it at a lower level with logic, with concatenation and bit twiddling, bit duplication, concatenation, and slicing, and blocking assignment statements. Everything else is pretty straightforward. We just have this nested ternary operator, looking at the opcode and then setting the output. We also use the $signed thing for the signed less than as well. So we had to use $signed for doing a signed multiply and a signed comparison. Everywhere else, the values were just interpreted as unsigned numbers for multiplying comparison. Oh, one other thing I want to mention too. We have another output called 0. There's a single bit coming out called 0. That's a flag that is true whenever the result is 0. So we're going to use that as a key for our branch if equal instruction. So if you execute a branch if equal, you're going to subtract the inputs A and B. And if they're equal, when you subtract them, the result will be 0. And then that 0 flag will indicate that we should take the branch. And if you're doing a branch if not equal, then you do the same thing, but just complement it.
Are you providing the branch logic?
No, that's something that you guys will have to do. Yeah. Okay, so we're going to give you the register file and the ALU. And then the instructions, there are 22 instructions in this lab that we want you to implement. Most of them are very similar to one another though. Like add and subtract are doing the same thing. The only difference is what the opcode is that you send to the ALU, right? Likewise, and I and or I, right? That's the immediate version of the bitwise. Those are just pretty much the same thing. The two instructions that are kind of the oddball ones here are load upper immediate, and this one, I believe that stands for control status register read and write. So these two are the ones that are strange. The LUI is the only instruction that uses the U instruction encoding format. And the CSRRW is just is just strange. You might have not seen anything like that before. So the reason we have that in there is because we want you to be able to build an application that's interactive through the FPGA board. We want to use the switches, kind of like you did in Lab 2, except the difference is, in Lab 2, you just created logic that you connected directly to the switches. But now we want to create a path to get the data from the switches into the CPU somehow. And when I say into the CPU, I mean into a register that you can then subsequently read from with an instruction and then number crunch on it, right? Likewise, we want to be able to take data in a register and put it out on the hex displays, right? Which will pass through your 7-segment decoders first, right? But we need an instruction that will trigger that transfer, right, between the register and the 7-segment displays. And we're going to use the CSRRW instruction for that. So that's an existing RISC-V instruction. But in RISC-V, it's not used for that. It's used for other purposes, other types of control and status registers. But we're going to use it we're going to repurpose it, okay? But we're still going to use the original encoding, for it. So that way, when you write this instruction in Mars, and Mars assembles it, we're going to use that same encoding that Mars is going to provide. And of course, Mars will recognize that instruction because it's a real instruction. Okay, so RISC-V has, one of the things that was nice about MIPS was that it only had 3 encoding formats for integer instructions. There was R, I, and J. RISC-V goes a little crazy with these instruction encoding formats. It's a little disappointing because I used to have the MIPS one memorized, the MIPS instructions, the formatting like memorized. But these ones they're a little bit too complicated. I always have to go back and check. So for this lab, we just have 3 though, but we're going to add additional ones later. Oh, by the way, just want to call this out. Notice that there's no jump or branches in here. Okay, that's intentional, right? Okay, so R-type, I-type, and U-type. The R-type is going to cover 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13 of the 22 instructions that you're going to implement are going to fall into the R-type category. That one is, the R-type, like in MIPS, you have 2 input registers and 1 output register. The problem is that the encoding format is a little weird because the opcode is last. Remember, it used to be first. The opcode in MIPS used to be the first 6 bits, right? Now it's the last 7 bits. So the opcode has grown from 6 bits to 7 bits, has moved to the other side of the instruction, and that function code, remember in MIPS the function code was 5 bits and now it's 7 bits. So how do we add bits? How do we have more bits? How is it possible that we have more bits in RISC-V than we did in MIPS? Anyone know? Well, actually, we added the function 3. We didn't have the secondary. So that function 3 is a secondary function code. So the function field is 7 over there, but then there's another 3, right? So it's actually 7 bits in total, but the 7 bits is not contiguous. Yes?
You have the shift amount.
Yeah, exactly. The shamped. Yeah, there used to be a shamped field. And that was one of the criticisms of MIPS. People were like, that shamped field is all zeros or don't cares 99% of the time. Because even when people are doing shift instructions, they're usually doing variable shift instructions. The shamped was only for a constant shift amount, right? So it was a waste. That was a boneheaded decision to put a shamped field. So we're going to repurpose those 5 bits by adding 3 for the function 3 and another 2 for the opcode and function code. Does that work out? We saved 5 bits, but then we added 1 for the opcode, 2 for the function code, and then another 3 for the function 3 code. Seems like we added 6 bits, but we only saved 5. Maybe I'm missing something. But anyway, the 3 registers are still 5 bits each, right? Okay, then there's the I-type. Now this one is also different from MIPS. You remember in MIPS there was a 16-bit immediate. In RISC-V they only have a 12-bit immediate. Why? To me that seems like that seems more limiting. Only having 12 bits. But I guess there was, somebody, looked, and that most immediates tend to fall in that 12-bit dynamic range. So, someone decided that 16 bits was too many for the immediate. So we deleted 4 bits from the immediate, but then we added a 3-bit function field, and we added 1 more bit for the opcode, I guess, is the trade-off there. Notice that the CSRRW instruction is in the I type. Why? Because the CSRRW instruction is addressing a coprocessor, I'm thinking MIPS is coprocessor. RISC-V calls it control and status register. That control and status register number is in the immediate, which means that you have access to 4,096 coprocessor locations with that instruction, which is pretty decent. So in other words, what I'm saying is that normally, you have 32 registers, but this instruction exposes another register file that's 4,096 registers, essentially. Okay. Of course, we're only using 2 in this lab. One is the hex displays and one's the switches. And then the LUI instruction is load upper immediate. We had this in MIPS, but it used the I type. This one uses a new type called U type that gives you a 20-bit immediate. Why 20 bits? Because 20 bits is the complement of the 12 bits, right, that we have in the other instruction. Okay? Load upper immediate is the only instruction I know of that uses the U type, and it takes the 20-bit immediate and it puts it into the upper 20 bits of a register. Now, one thing too, notice this is important. The MIPS wrote to a different register field, depending on if it was I type or R type. You remember that? It was an RT field. Anyway, you'll notice that the RD, check this out, the RD is in the same bits in all 3 instruction encodings. This is really nice because in MIPS, you had to add extra hardware to figure out, what your right register was. But in this case, they've kept it, it's always an 11 down to 7. So that saves some hardware.
Is it still opcode is 0 for the R's and you look at the
No, that's a good question. Yeah. Yeah, I almost forgot about that. Yeah. In MIPS, all the R-type instructions have a 0 opcode. Yeah, that's not the case anymore.
Control's easier.
Yeah. Yeah, this one has opcodes are all, it's more difficult to see patterns in the opcodes that they assign for RISC. Although I'm sure they're there, I haven't looked at it closely enough. Okay, then there's the CSRRW instruction. So the way we used to do this with MIPS, by the way, just to give you an idea of why we switched to this, is we used to reserve register 30. We used to create a special register file where if you wrote to register 30, it would update the hex displays. And if you read from register 30, it would give you the switch values. Right? But that was wildly confusing for everyone because it meant that the read and write behavior of the register 30 was different. And it was kind of arbitrary. No one was happy with that. So when we went to RISC-V, we got rid of that and we just used this CSRRW instruction. The problem is that the way this really is supposed to work is, if you look in the RISC-V instruction set, it says that you take the value of the CSR register that's indexed, that's addressed by the immediate field, and you put that into this T, temporary, and then you take whatever's in the RS1 register and you put that into the CSR register, and then you put T into the RD register. So what does that mean? What's happening there? This is doing an atomic swap, is what this is doing. It's taking whatever's in the special register and whatever's in register RD, and it's swapping them. It's taking whatever's in the special register and putting it in the destination, and whatever was in RS1, it's going to put in the special register, right? So it's reading and writing at the same time this special CSR register, right? It's kind of, doing the swap. The problem is we don't want to do that in this lab. We just want to have a separately defined behavior for the LEDs and the hex displays, right? If you do this, if you apply this instruction on the hex displays, it's an output only, right? Because you can't read the hex displays. I mean, I guess you could. You could read whatever was last written, I guess, but we're just treating it like the hex displays are write only, right? And the switches are read only. You can't write the switches unless you had like an actuator on there that would flip the switches, on the board without you touching them, right? Which we don't have. So, so the way we're going to do this is actually this is, so we have, in this case, I'm showing register 0 is the switches and register 2 is the hex displays. Depending on which one you write, this instruction will either read the switches or write the hex displays. Make sense? Now, notice the weird formatting here, though, for the assembly instruction. The immediate value is in the middle. It's the second thing specified, right? So you've got RD, comma, the CSR register, which is effectively a 12-bit immediate value, comma, and then the source register, right? This is strange. I don't like that. But that's the way they chose. I would always put the immediate last if it were me, just it would be consistent with all the other immediate instructions, right? Like for like an add I. If you do an add I, the immediate is last, right? But if you do a CSR, the immediate is second, right? Why? I don't know why they did that. Also, the values that we want you to use is actually not 0 and 2. We're going to use F00 and F02. Just a different choice there. We also have a modified version of RARS. If you download RARS from the RARS GitHub and you try to use this CSR instruction the way that we're using it, I think you get an error. But if you download the RARS from Dropbox, we modified it so it recognizes those two special register values for CSR and it lists those in the register panel for the hexes and the switches. Now, that doesn't mean you have to use you can still use the original RARs, but then you'll have to, replace those with load immediate, right? Like you have to tweak, you have to hack it a little bit more, right? You guys with me? Okay, yes?
So all that talk, that's logic we have to write.
Yes.
And is it going to tell us which stage of the pipeline?
Yes, I'm going to show you all that. Yep, yeah, I'm getting there. Okay, so the way we'll organize this, just to give a little context. So you have the top.sv, right? And inside, so top is the FPGA, and then inside top, you guys have your 7-segment decoders, right? You already put those in there for lab 2, right? So we want to reuse that code. We don't want you to have to rewrite anything. So you leave those in there. And then you put your CPU inside of top, and the CPU will have a 32-bit output, which we call GPIO out or hex out or whatever you call it, right? There'll be a 32-bit output that will feed into the 7-segment decoders, which will then go out to the 7-segment displays, right? So basically your top will contain your CPU and your 7-segment decoders. Now in this case, I'm showing the RAM, the instruction memory in here as well, but organizationally, this will be inside the CPU, right? I just showed it. Logic, now you might say, why'd you show it externally then? What's the point of that? Well, because normally the instructions are not in the CPU. Well, I say that. I mean, I think most of you now probably have experience with programming like Arduinos, microcontrollers, where you actually do put the instructions in the CPU. But traditionally, the instruction RAM was separate from the CPU, right? Logically, right? But in our case, we're going to just put it in more like the Arduino style, right? Does it make sense? So the instruction RAM will be inside the CPU. So the only thing in your top.sv will just be your CPU and your decoders. But you can organize it however you want. I guess it's just a suggested. That's what we suggest. Okay, so how do you get started? Everyone always asks, what's the best way to start this? So This is a good starting point. So this is a CPU, I don't know how readable that is, but this is a CPU module. And right now, there's just an input clock and a reset _n. Now, why _n? Traditionally in this class, we use one of the buttons as the reset. And those buttons are active low, which means when you push them, they're 0, right? So if you want to connect the button directly to the reset, you have to use active low logic. All right, so that's why you have reset _n. Now, you might be thinking, do we need a reset? Technically, in this lab, you don't, because we don't have any branch instructions. But we want you to have the reset in this lab so you can have it for the next lab, right? Okay, so now this is where we get into a little bit of coding style. This is something that my former student, Charles, would not have liked, because you'll notice that at the beginning of the CPU, I have an initial statement that, actually the first thing I have is the instruction RAM. Remember that when you declare a 2D array in Verilog, you have to put columns and rows instead of rows and columns like every other programming language, right? So the 31 to 0, which is the width, comes first, the depth comes next, and this is 4,096 entries deep. Then we have this initial statement that's going to initialize the ROM with a file that you're going to get directly from RARS, right? How weird and coincidental is it that RARS just happens to save a file that matches what's expected here in Verilog? You have to save it. So you go to dump memory in RARS and you tell it you want a hex file, and it'll dump a hex file, which is the hexadecimal version of your program, into a text file which is compatible with this initial statement, right? So all you have to do is export your code from RARS, and then it will automatically be read in here. And then on the FPGA, it'll get included on the FPGA through programming the ROM, which happens when you program the FPGA. And the ROM gets included in the bit stream when you compile your synthesizer design. Now, some people say, well, that's a bad way to do it, because that means that anytime you change your code, if you change your program, your RISC-V code, then you have to resynthesize your whole design to get that code into the bit stream, which is then programmed into the FPGA. We used to have a better way to do that. There is a better way to do that. The Intel FPGAs, this is something that the other company, AMD, doesn't offer, believe it or not. The Intel FPGAs have this cool feature called in-system memory programming, where you can actually, there's a tool called the in-system memory content editor. You can actually program, you can take your RISC-V code and you can put it in the instruction memory after the FPGA is programmed. That's pretty cool. That's neat. Is you can load a new program without having to recompile or resynthesize or reprogram the FPGA. But it takes a little effort to make that happen, and nobody in this class ever used that because we don't really have a need in this class to, reprogram the processor, right? So we used to tell everyone to do it that way, but it was more trouble than it's worth, because generally speaking, once you put your code in there and then the program stays static, and then you spend all your time debugging the hardware, right? So there's no reason to change the program, right? The program is basically like a test vector almost, You put it in, you don't change it. So we don't have that ability, but it is possible to do it in a nicer way than this, right? Does it make sense, you guys? So what I'm saying is that we're baking the program into the hardware, essentially. And then we have the program counter. Now, notice I call it PC_fetch, and there's a reason for that. I'll get back to that in a minute. But that's the program counter. We initialize that to 0 when you program the FPGA. And the instruction _EX is the currently executed instruction. And then there's an always. This is essentially the fetching part of the processor. So always at pause edge clock, if there's a reset, set the program counter to 0 and set the instruction to 0, which is a no-op. And then if you're not resetting, then you always increment the program counter. So the program counter is always marching forward every cycle, you're not resetting. And you're accessing the corresponding instruction here and putting it into the instruction underscore EX. Okay? So this is your fetch stage. Now, we don't have any way to change the flow of the instructions because we don't have branches and jumps yet. So you might say, well, wait a minute, what happens when it finishes running the program then? The program counter will roll back to 0 like an odometer, right? And it'll keep cycling through the program infinitely. So whatever program you put on here will automatically be put in an infinite loop because the program counter is rolling back over to 0 and then it keeps repeating.
It's going to fetch zeros if we load. We have to make sure that the ROM has zeros where there's unused instructions.
Good question. Yeah, no, it does that automatically. Yeah. So if you don't have to put all 4096, you don't have to zero pad. You don't have to zero pad it. Yeah, that's a great question though. By the way, the zero instruction in MIPS was an add I. But in RISC-V, it's actually a shift left logical. It does a shift left logical. But the destination register is 0. So if you execute a no-op, it actually writes the register 0, which produces, that doesn't do anything, doesn't change the registers. Any questions about that? So you can use our code. Oh, now the reason I mentioned that this is something that Charles wouldn't have agreed with is because the fetch logic is not in a module, it's inlined. So pretty much I just vomited out the fetch logic in the same module as the CPU, right? Some of you may look at this, depending on how much of a stickler you are for like coding style, you may look at this and say, well, shouldn't the fetch be in a separate module? Why is it just inlined? Well, I inlined it because it's easier to show on a slide, obviously. It's easier to present, right? But if you want to, you can outline that into a module, right? Because it probably should be a submodule logically. The problem, though, is every time you outline a module, you have to connect all the ports, right? Now, you don't have to do any port connections here, but if you create a module, you got to start doing all your port connections, and it adds a lot of overhead. And it's a potential for introducing a bug, too.
Do you have to weigh that against when you add branch in, though?
Yes. Oh, sure. Yeah, it complicates because you're going to add additional signals for the branch and the stall. Yeah, so it's going to add a lot of I/O if you outline the fetch. That's another reason why I left it in. But this is a decision you have to make as a Verilog programmer, is what to outline, what to keep in separate modules. Some people may say if you outline it, it'd be more readable. I don't know if that's the case. Maybe. I don't know. Okay, so just shows the overall design, just to revisit this. So we have simtop.sv, so that will still be our simulation top-level module, no inputs, no outputs. We're going to have top.sv, but remember that top already has the 4-bit key input and the 18-bit switch input. You guys just didn't use the key before, right? Use the switch. The switch input is going to have to be fed. Right now, you have switches going straight out to the decoders, right? So right now in Lab 2, you short circuit the switch to the decoders. We're going to break that connection because now the switches have to go in the CPU, and then the CPU will have a separate output that'll go into the decoders, right? Notice that I call this now IO0 in and IO2 out. I keep changing. Don't get confused, but it doesn't matter what you call these. The point is you have a GPIO in and a GPIO out. You could call it switch in or hex out, or yeah. Don't be confused by that. I refer to those as different names in the lecture in different slides. Make sense? Okay. So you can see how Lab 2 was designed to get you kind of used to that structure. Okay, so how are we going to actually fetch and execute instructions then? So you might remember from 2.12 that you can design a CPU to be a single cycle CPU, meaning that each instruction is executed in its entirety within one cycle. In fact, some CPUs work that way. The microcontrollers often work that way. So an ARM Cortex M0 probably, I don't know about the later, bigger ones. Atmel processors, like the Arduino, a lot of them do execute instructions in a single cycle. Some CPUs are multi-cycle. Multi-cycle CPUs take advantage of the fact that different instructions require a different amount of workload, different amount of data path operation. So a multi-cycle CPU allows you to execute one instruction at a time across multiple cycles, but the number of cycles can vary between instructions. So if you have an instruction like a branch, it will be done in 3 cycles, but an instruction like a load instruction takes 5 cycles, right? So that way you can have a very fast clock, right? Whereas a single cycle CPU, your clock speed is going to be slower because it has to be long enough to accommodate the most complex instruction, you know, the instruction with the most going on, right? The most data path, right? Which is usually a load. Guys with me? So single cycle is simpler but slow clock. Multi-cycle has to be controlled by a state machine across multiple cycles. I mentioned to you earlier that if we had created a divide instruction, if we add a divide instruction, we would have to make a multi-cycle for the divide, right? The divide would have to be span multiple cycles, right? Because I don't think you can do a divide I don't think any CPU does a divide in 1 cycle. That's totally unreasonable, right? A lot of CPUs don't even have divide instructions. They just emulate that in software. What are we doing? We're going to do a pipeline CPU. Pipeline CPU executes multiple instructions in parallel. It has multiple in-flight instructions at one time, and you might have learned about that in 212 if you got far enough. So in the 212 class, you know, when they use that textbook, they usually present the CPU as a 5-stage pipeline. There's fetch, decode, execute, memory, and write back, right? That way, when the pipeline is filled, as it usually is, you have 5 instructions being executed at the same time at different points along their execution path, right? At different stages in their execution, right? At different levels of progress through their execution, right? That's really what we should do, but we decided to simplify things to 3 cycles in this class. We're going to do a 3-cycle. Now you might say, well, how do you go from 5 cycles to 3? Well, we just merge together the middle 3 cycles. So decode, execute, and memory. Of course, memory doesn't exist because we don't have any memory instructions. So decode and execute are together. We just merge those into one stage called execute. Is that a good idea? We never really examined like what the impact of that decision is on clock speed, but we do it so you can learn, you know, sequential logic design basically, without getting too. 5 stages gets a little tricky in the code, especially if you're jumping straight in like we are, you know. Does that make sense? So what's decode? What happens in decode? Do you guys remember decode? Yeah. Yeah, that's right. Yeah, so the instruction comes in fetch, and then in decode, it breaks out the instruction into control signals, right? But it also accesses the register, reads the registers too. Okay, so this is a single cycle where if you have 3 instructions, so we got gray, blue, and purple. Gray comes first. Then gray would be executed in cycle 0. Blue would be executed in cycle 1 and purple in cycle 3. Everything required to execute those instructions would happen in one cycle, right? That's a single cycle. That's how the microcontrollers work. In our case, we want to, the concept here is that we want to, the concept is that single cycle is too slow. Our CPU should be faster than our Arduino. That's the idea. So to accomplish that, we're going to break up the execution into multiple cycles. So we're going to execute each instruction over 3 cycles. So we're going to fetch in 1 cycle. And by the way, if your instruction memory is synchronous, you have to fetch in 1 cycle. The only way to create a single cycle CPU is if your fetch is asynchronous, right? You have to be able to fetch within 1 cycle. So 1 cycle to fetch, then another cycle to number crunch it, you know, branch resolution, ALU, whatever you want to do there. And then the 3rd cycle write back. We need a whole cycle for write back. Well, I shouldn't say we need a whole cycle, but we're going to allocate a whole cycle for write back. Okay, but then the problem with this is that now we want to also have other instructions that are executing at the same time. So while the purple instruction, which is the third instruction, is fetching, we're going to be executing the blue instruction and writing back the gray instruction, right? So whatever instruction comes sooner is going to be, well, this is always weird to think about this, but the instruction that was fetched sooner will be later in the pipeline. That used to confuse the heck out of me. Whoever the youngest, sorry, the oldest instruction, rather, I should say. So the first instruction executed will be the later one in the latest one in the pipeline, right? Okay, so we're going to have 3 instructions going at one time. Now, how do you design something like this, though? How does this work, Verilog-wise? Well, I'm not sure how it's usually done, but the way that we came up with for this class is we add a suffix to the signal names to designate which stage those signals belong to, right? So I mentioned earlier that when I showed you the code back here, we have this thing called PC_fetch and instruction_EX. The reason they're named that is because whatever value like when you simulate and you put your cursor down, whatever value is in PC fetch is referring to the instruction that's being fetched, which is a later instruction than whatever's in instruction EX, right? In other words, instruction_EX is the instruction being executed, but the address in PC fetch is the address of the instruction being fetched. Those are 2 different instructions, right? And so we add these suffixes to the end of every signal to designate where they are in the pipeline. It's going to make it easier to debug, right? So if you're debugging, you put your cursor down, PC fetch might be 12, right? It means you're fetching instruction 12, but the instruction EX is going to be 11, right? It's going to come because 11 was before 12, and so that's further along in the pipeline, right? Now you can imagine if you had a 5-stage pipeline, you'd have to have 5 different, like every signal would belong to one of 5 stages, right? That would get complicated. It's doable, but we wanted to simplify it a bit, right? But what that means is that how do you go from one stage to the other? The way that happens is through an always_ff at pos edge clock. So anything you assign in an always_ff will be assigned, say you're assigning _EX, but the inputs are _fetch, right? Or likewise, write back. If you assign something, any signal assigned with a _WB suffix should have all of its inputs, the right-hand side of the assignment should be _EX, right? Because those always update their outputs on the clock edge, right? And so whenever those always activates, you're always pushing from one stage to the next, right? So the left-hand side of an assignment should be one stage later than the right-hand side of the assignment, right? And so you should be able to verify that in your code. Now that's only for always at pos edge clock. Now you could also have always at star or always_com, in which case the left and right-hand side of the assignment should be the same stage, right? Because they're combinational. But if it's sequential logic, if it's a clocked always statement, you make sure that you're always pushing from one stage to the next stage. Make sense? We came up with that idea. I'm pretty proud of that idea. I learned that when we used to teach this, we didn't really have a way to organize the signals. So simple idea, but I think it helps a lot. Okay. Okay, so let's start going through some of the designs. So what's happening in fetch? So we have the instruction memory, which what is the instruction memory? Well, when I say instruction memory, I'm just talking about really like those 2 lines of code, those first 2 lines of code, right? Those first 2 lines of code in the CPU module constitute that big box that says instruction memory. So what I'm doing is I'm now showing this in a structural, like block diagram schematic capture view, right? But you remember that this just all corresponds to text in Verilog. So you've got the instruction memory, and its address is hardwired to PC fetch. PC fetch is an incrementer, so it just has its input is the old PC add 1, increment 1. And then when the instruction comes out of the instruction memory, now remember the instruction memory is synchronous, so by going from PC fetch through the instruction memory, now it becomes instruction EX, right? Because this is an always _FF at pos edge clock. That's how you're implementing the read behavior of the instruction memory. If we wanted to make an Arduino style single cycle processor, then that would have to be combinational logic, right? It would have to be asynchronous, right? But because the fetch is a whole clock cycle, it's always _FF. And then once instruction EX comes out, it needs to get broken into fields, which you can give names to. Now this is something else that my former student, who was a stickler for a coding style, he was really into this idea of creating a module that he called the decoder, which does nothing logically, I mean hardware-wise, but it renames all of the fields of the instruction. He gives them names, right? So for example, the instruction is called instruction EX, right? And then if you look at 31 bits, 31 down to 25, 24, whatever 7 bits is, right? That's the function 7 code, right? But instead of having to always refer to those bit fields, why not just rename it as function 7 _ EX? Right? Which means you're now going to have 2 names in SystemVerilog referring to the same 7 bits, right? Which seems wasteful, but it doesn't cost you anything in terms of the hardware. You're just creating an alias, right? So he did that through the decoder. He called this thing the decoder, right? But it's not really accurate. It's not really decoding anything. It's just renaming signals. Make sense? This is better than the way I did it. I just always use the bit fields. But that's, if you don't memorize all those bit fields, then it gets confusing. Okay, and then as Laura mentioned, you're just going to plug the RS1 and RS2 directly into the read address 1 and 2 on the register file. There's no mux there, just straight connection. You're just shorting them. But, and this is the part that gets confusing, the write address, that's the RD field, but not directly, because the register file is one module, but its functionality is split between 2 distinct stages. So there's one module, but depending on what port you're talking about on there, you could be talking about different pipeline stages. So the write address port belongs to the write back stage. So you don't want to take the RD field from the execute stage and plug it in. You need to add a delay register, pipeline register. This is nothing, but it doesn't do anything. It basically renames the signal, just like the decoder renames the signal, except it has a pos edge clock in there. So it's a clocked rename. So it's going to take whatever the current instruction's RD field is, it's going to send it 1 cycle into the future, basically. It's by delaying it 1 cycle, right? So in the next cycle, 1 cycle into the future, I'm going to have an RDWB that's going to reflect what the old RD was in the previous cycle. So that's just, I designate that with a little box that says R, stands for register. What is this in the code? It's 1 line of code. Always _FF at pos edge clock. This equals that. That's it. That's all you need. That will create a register. Now some people like to put all their registers in one big always block, as opposed to individual always blocks. That's up to you. It's a coding style thing. I usually just put them as a separate always, but you can group these, you can group all your delays into one big always if you want. Does it make sense? So what does that bypass, how does that bypass play into this? What that means is if you have an instruction that reads a register that appears after an instruction that writes a register, then you'll be reading and writing that same register in the same cycle, Not from the same instruction, from two different instructions, but they're at different stages of the pipeline, right? So whatever instruction came second will be reading. The instruction that came first will be writing, but they'll be doing it at the same time because of the pipeline. And that's when that bypass will activate inside the register file. Okay? Because if you read and write the same register inside the same instruction, you will get the old value of that instruction. Like if I have one instruction, if I say add register 2, register 2, register 2, right? It'll give you the old version of register 2, right? But if you have two consecutive instructions where one writes register 2 and the next one reads it, then it will activate the bypass path. Two different instructions, right? Make sense? Okay, so this is the thing I was talking about with the code. So you're going to write your code in RARS, and you assemble it, and then you go to File, Dump Memory, and it'll bring up this dialog box, and you just say that you want to dump the text, and the format should be hexadecimal text. And you hit OK, and it'll ask you to give a file name. Most people, it doesn't matter what you call it. Some people call it program.rom or hexcode.txt. Doesn't matter. Just put it in a file, and then use that same file when you initialize your instruction memory here. Just make sure you dump it to your project directory. And that way, your assembly code will automatically get, not automatically, but it will be converted through RARS to machine code. So you don't have to hand translate it, right? It's done through RARS. RARS is going to do the assembling for you, but then you'll still get the corresponding hex code in your hardware, right? And then when you're debugging your hardware in Model Sim, you can have RARS up at the same time, and you can walk through it in RARS as your CPU is executing it. You know, if you're trying to track down an error. Yes?
Why does Verilog read in hexadecimal text files if it's just like a raw binary file? It's like raw binary seems a little more like...
Yeah, that's a good question. Well, I think it's because it's designed primarily for test vectors, but that's a good question. There might be a version that does read in a binary file that I'm just not aware of. But the $readmemh, so there's a $readmemh and $readmemb. One's hex, they're both text files. The difference is what's in the text file, if it's hex or binary, right? But they're both text file formats. That's expected.
Okay.
But there may be another dollar function that reads it binary. Yes?
Do we have to get our code from the previous lab running on the first?
No, that'll be the next lab.
So like,
Yeah. Yeah, good question. So this one, I'm going to give you a test bench. I'm going to give you a test program that tests each instruction at least once. Is that enough? Probably not. But you got to run it. You got to at least run every instruction once, right? Then there's a second program we're going to ask you to write that's going to be a binary to base 10 converter, which we're going to write from scratch in this lab. And then in the next lab, you're going to bring in your square root code and tie everything together. So we're going to do a binary to base 10. So the objective of this lab is you're going to flip the switches on the board, and it's going to give you not the hex representation, but the decimal. So if you put the last 4 switches, 1, 1, 1, 1, that's 15, right? But in lab 2, it wouldn't show 15, it would show F, right? But in this lab, we're going to have the CPU do the translation, so it'll actually say 1, 5 in base 10 instead of F, right? Which we're going to do again we're going to rely again on fixed point to do that, because normally to do a binary to base 10, you have to have a divide and a modulo for that, which we don't have, but you can approximate it once again with fixed point like we did before, just to give you a preview. Okay, so I think I got far enough along for you guys to get started. I didn't finish everything yet, but if you grab the Lab 3 description from Dropbox, it's very long and detailed. There's a lab sheet. It's long, but it includes all of the instructions and their encodings at the end in an appendix. I think that's most of it. the first part gives you some hints, and it's very detailed. I recommend that you read the lab sheet. It's basically a description of what I've told you today, but it's in text form, and it'll give you some hints and show you how to get started. And then you can download the project skeleton. Oh, do I have that? Actually, we're using the same. You're using the same project skeleton as last time, Lab 2. There's nothing different. The same one, right? Because you can build this on Lab 2. You don't have to, like I said, you just have to disconnect. You have to disengage the switches from the 7-segment decoders.
Are we going to be doing a demo for that?
Yes, there's a demo for Lab 3. We're going to ask you to, put in the value 31, and you're going to flip the switches, and then we should see 31 on there, right? So you're going to put a binary 31 on the switches, but it should show a decimal 31 on the hex displays is the objective. But this time we get to have all the hex displays, I think, 30? Because if you put all the switches up, it's 262,000. Oh, no, sorry, that's still 6 digits, never mind. But the next lab will be able to use all the hex displays. Digits, rather. Yeah. Okay, so I think you're good. If you have any questions, let me know, or the TAs know, but I think you have enough to get started. I'll finish this lecture next week.